All right, hi everyone. My name is Apisa, and today I'm going to speak about in the moduli space of abelian differentials, big invariant subvarieties come from topology. And this, as it says, is joint work in progress with Alex Wright. I'd also like to thank the organizers right off the bat for inviting me to come join this conference. So to start off, I want to talk about a simple topological puzzle. And so it begins with a motivating question. So motivating question one. So given a surface S that is a branched cover, so in this case a holomorphic branch cover of a torus, and say branched over a single point via the map F, we can ask the following question. So this is going to be our example of such a surface. I'll explain that in a sec. So we could say, let gamma be the collection of simple closed curves on S, which we'll abbreviate from here on out as SCC, that are connected components of preimages of simple closed curves on our torus T. So let's call that torus T. Okay, so first, let's explain why this picture that I drew here is an example of the setup in our motivating question. So this surface here is S. This map that we've drawn here via an arrow is a 3-to-1 cover of the torus, where each of these squares goes down to this torus. And I should also say that when I draw polygons like this, I'm tacitly assuming that opposite sides of them are identified. So in this case, we would make all of these side identifications. And when we do, S will become a genus 2 surface. And also tacitly, we make these side identifications, which makes T into a flat torus. So this picture, taking all of the squares to the square here on the flat torus, is a 3-to-1 branch cover branched over this point, which I've drawn as a blue dot here. And so gamma is the collection of simple closed curves, which are connected components of the preimages of simple closed curves on T. So for instance, if this is a simple closed curve, call it maybe gamma, then I look at its preimages. So I have this one A, and I have this one here, which is B. I take their connected components and I throw all of those curves into this set gamma. So in this case, A and B would both be elements of gamma. And then the question is the following. So is it the case, does gamma generate all of the homology of S? So in this example that I've drawn here, the answer to that question is yes, but the question is, in general, if we have a branch cover of a torus, is it the case that the collection gamma that I've described here generates all of first homology? So let's also be careful and say first homology. Okay, so the answer to this question is the version I'm going to present due to Forney, and the answer is no. And the example that we look at is called the eierlegende Wollmilchsau. And for ease of writing, I'm going to call this just EW for the rest of the talk. So there's a picture of it right here. So as it says, this figure was produced by Pat Hooper and Barack Weiss. So this surface that we see is an 8-to-1 cover of a flat torus. So we see 8 squares here. We send each of those to the square torus, and that gives us this 8-to-1 cover. Okay, so what's the idea, though, that this is a counterexample to the idea that gamma must generate all of first homology? In other words, why does gamma, for this very specific cover, not generate all of first homology? So here is the idea. The idea is that on a flat torus, simple closed curves correspond to cylinders. And moreover, the eierlegende Wollmilchsau has what's called the geminal property. And so we're going to revise what this property means later when we're working outside of the context of torus covers, but for now, provisionally, being geminal will mean the following. So i.e., for every cylinder, and maybe we'll give ourselves a tad more space. So for every cylinder C, there is a twin cylinder, C prime, that is parallel and isometric to C, and so that C and C prime cover the full surface, the full Eierlein-de-Wollmich cell. Okay, so let's see why this geminal property has anything to do with the question that we just posed. So we said that if I have a flat torus, I could think about a simple closed curve, like this one, as corresponding to a cylinder. How do we do it? We'll pull the simple closed curve tight in this metric to a geodesic, and then by virtue of having a flat torus, we'll know that the torus is foliated in that direction by parallel curves. That's the definition of a cylinder. So if we see what the preimage of that cylinder is, well, in this case, for the horizontal cylinder, this red cylinder is one of the preimages, and this green cylinder is the other. And the geminal property implies that these two cylinders are going to be homologous to each other. And similarly, if I took my torus and I took a curve, say one that goes like that, the cylinder is foliated by parallel curves in the direction of the red curve here. And what that becomes on my Eierlein-de-Wollmich cell, when I lift it, I get this cylinder here, which I'll shade blue, and its complement, which we have guaranteed, is isometric, parallel, etc., which is this unshaded white cylinder. And so the geminal property implies that whenever I see one cylinder, in fact, the preimage of any cylinder on the flat torus just consists of two homologous cylinders. And so in particular, what this implies, so the geminal property implies that the subspace of homology generated by gamma is two-dimensional. You can think of it as the Poincare dual of the pullback of the first homology, cohomology rather, of the torus. Okay, so I want to end this first section with an open question. So open question 2, what are the geminal square-tiled surfaces? Okay, so that's a fully open question just using what we've discussed here, and hopefully this discussion of what it means for a square-tiled surface to be geminal will motivate what is going to come in the remainder of the talk. All right, so now I want to switch gears and talk about dynamics on the moduli space of translation surfaces. So first I want to talk about how I think about translation surfaces, or equivalently holomorphic one-forms. So let's say a quick word about that. So first, every holomorphic one-form on a Riemann surface, which is just a surface endowed with a complex structure, can be presented as a union of polygons with sides identified by translation. And this is also called a translation surface. So what's an example of that? We just saw an example of a surface S that was an 8-to-1 cover of a flat torus. A flat torus, of course, has a unique invariant holomorphic differential up to scaling on it. If that's pulled back to S, then up to scaling, the holomorphic one form corresponding to the pullback of dz by f will be this collection of polygons with sides identified by translation. So the way that we'll be thinking about holomorphic one forms on Riemann surfaces is with this very geometric picture, thinking about them as polygons with sides identified. So this perspective is quite powerful if we say that omega mg is going to be the collection of all Riemann surfaces x and holomorphic one forms omega. So if you like, this is a Riemann surface, and we'll say its genus is G, and this is a holomorphic one form on X, then this is the same thing as polygons in R2 with sides identified, I won't write it all out, by translation. And quite nicely, since polygons in R2 are in R2 in this construction, there's a GL2R action on R2, which in turn induces a GL2R action on this space of holomorphic one-forms on Riemann surfaces. So the two lives that a holomorphic one-form on a Riemann surface lives means that its moduli space, or the collection of all examples of this object, emits a GL2R action. And so what does this GL2R action look like? So if I drew a holomorphic one-form by these three squares with sides identified, recall our convention that opposite sides of the polygon are presumed to be identified if they're not marked. And we acted on this by the matrix 1, 1/2, 0, 1, then we would shear the picture to replace our polygons, or rather our squares, with now parallelograms, which are identified in the order indicated by this figure here. Okay, so thinking about holomorphic one-forms on Riemann surfaces as polygons means that the moduli space of translation surfaces or of holomorphic one-forms has this GL2R action. So now you can ask a dynamical question. So I'm gonna ask the question of what does the orbit of a Riemann surface X and a holomorphic one-form omega look like under GL2R? And the answer to that question is given by the theorem of Eskin-Mirzakhani and Mohammadi when G is bigger than 2, and by Kurt-McMullen when G is equal to 2. And it says the following. So the GL2R orbit closure of any point in the above dynamical system is a manifold, which is quite a surprising property from the perspective of dynamics, when often you expect pathological closed sets to be possible orbit closures, as often happens with GDs of flow. Even better, this manifold by work of Simeon Philip, and again, McMullen in genus 2, is an algebraic variety. And so a question that you can ask, fully open, again, open question 3, is what manifolds are orbit closures? And that will be the focus of the rest of this talk. So now I want to partially answer the question that I posed in question 3, and I want to discuss a little bit about the structure of these orbit closures of the GL2R action on the moduli space of translation surfaces. So first of all, I want to say that there is a coordinate system on the moduli space of translation surfaces, so that near any holomorphic one form, which we thought of as a collection of polygons, the coordinates are given by recording the edges of the polygons as vectors in R2. So for instance, on this surface up here, which we can think of as some sort of Riemann surface together with a holomorphic one form, we have 6 polygons here. Their edges have been marked, recall the convention, opposite edges identified to each other. If we specify this edge too, and then specify the values of A1 through A3 and B1 through B3, as well as C as vectors in R2, then we have completely specified what the translation surface is. And so that's the coordinate system. The coordinate system would be, for this particular example, specify exactly what these vectors are. And then that will in turn tell you what the translation surface is. And so Eskin-Mirzakhani and Mohammadi said the following: any GL2R orbit closure, which remember is a manifold, is locally described in period coordinates by real linear homogeneous equations. So for example, you could think of your affine invariant submanifold M, which perhaps is the orbit closure of this X omega, as being given by the equations AI equals BI for all I. These are real homogeneous linear equations. If you made this assumption, then you would notice that all of the surfaces inside of M are actually covers of lower genus translation surfaces. If you demand that AI equals BI for all I, then it's fairly straightforward to see that your surface admits a double cover of this genus 2 surface. So this would be A1, this would be A2, this would be A3, this edge down here, and this would be C. And so we see that some affine invariant submanifolds imply that every single surface contained inside of them is a cover of a lower genus translation surface. This leads to a question of Mario Mirzakhani which is essentially where I drew the title from my talk. The question asks the following: if an orbit closure is sufficiently big, then must it be a locus of covers? And what does sufficiently big mean? So the actual conjecture says that the rank of M is bigger than G over 2. G is the genus of the surfaces being parameterized. I don't want to describe what the rank of an affine invariant submanifold is. So this is implied by a much more understandable condition that the dimension of the affine invariant submanifold is bigger than 3/4 of the dimension of the moduli space of translation surfaces in which it's contained. So if an orbit closure is sufficiently big in this sense, then the conjecture is that we have to be a locus of covers. And in fact, the conjecture is that we're a locus of double covers. And the theorem that I want to talk about today, so theorem 1, due to me and Alex Wright, is with regards to this question, yes. If your orbit closure is sufficiently big, then you must be a locus of double covers. And I should say that there is one caveat. So obviously a caveat is that this is work in progress. And at the moment, this work in progress requires that rel, which is another technical parameter of the orbit closure, be equal to 0. But we're in the process of removing this condition. Given that this result holds for rel equals 0, it should be a fairly straightforward process. So to approach the previous theorem that I just described, I want to talk about what a cylinder dilation is and what a geminal orbit closure is. So to begin, given a collection of disjoint cylinders C, we'll say that a cylinder dilation is a path in the space of translation surfaces given by stretching all of the cylinders in C, changing their heights the same amount, so scaling them by the same amount, while keeping their complement fixed. So I've drawn 3 examples here. So here we have the surface that we were just considering. We see that there are 3 horizontal cylinders labeled C, C prime, and D. In the first picture, I've dilated only C while fixing the rest of the surface. Recall that in the orbit closure that we were just considering, we said that AI is equal to BI for all I. By dilating C, we see that we have violated this condition. A1 does not equal B1, and so the resulting surface does not belong to our orbit closure M. If we consider this example, where we take C and C prime and we dilate them, this time shrinking them, we do so by the same amount, and so on this new surface, A1 and B1 are identical, and this cylinder dilation still belongs to M. Similarly here, if we take the final cylinder, D, and we stretch that out, well, there are no equations in M which relate D to the rest of the periods, and so this surface remains inside of M. So these are 3 examples of cylinder dilations, and we see that the cylinder dilation may or may not cause us to remain in an orbit closure. So this leads us to the definition of what it means for an orbit closure to be geminal. So we'll say, given an orbit closure, M, say that M is geminal if for every surface in M and every cylinder C on that surface, either the cylinder dilation in C remains in M, or, so that would be, as in the third case, C would be, in that case, like D, dilating it causes us to remain in the orbit closure, or there is an isometric parallel cylinder, C prime, so that dilating C and C prime remains in M. And this, of course, is like the second example. With our, given that we satisfy the equation, A1 equals B1 and A2 equals B2, the cylinders C and C prime are parallel and isometric to each other, and we saw that dilating them remains in M. So an orbit closure is called geminal if either you can dilate every cylinder and stay in the orbit closure, or every cylinder has some sort of twin. And so the theorem that I want to talk about is the following. So this is still due to me and Alex Wright. It says if M is big in the sense of the previous slide, then M is geminal. Okay, so that's one collection of examples of geminal orbit closures. They're the big orbit closures. Other prototypical examples are the following. So examples of geminal orbit closures. The prototypical example would be double covers. For a double cover, every cylinder, as we saw above, this after all is an example of a locus of double covers, every cylinder on the surface being covered lifts either to a single cylinder, as is the case with D, or to two cylinders, like the cylinder whose preimages are C and C prime. And so for that reason, loci of double covers are the prototypical examples of geminal orbit closures. Another example would be the orbit closure of the Eierlegende Wollmilchsau that we saw in the beginning. We said that given any direction on that surface that had a cylinder in it, there was an isometric parallel cylinder that covered the entire surface. Dilating both of those cylinders is the same as just stretching the surface in a given direction, and dilation in a given direction is certainly inside of GL2R. So the Wollmilchsau is sort of an exotic example of a geminal orbit closure, and these double covers are more simplistic examples of geminal orbit closures, and of course being geminal is related to the orbit closure being big. One final place where you see geminal orbit closures coming up is studying the complex geometry of Teichmüller space. So there's a theorem of Markovitch and Gechtman which says the following: let Q be a stratum of quadratic differentials. So I haven't introduced what this is, so if you don't know these words, don't worry, we won't use them in the sequel. So let Q be a stratum of quadratic differentials, and let M be the collection of quadratic differentials in Q whose Teichmüller disks are holomorphic retracts of Teichmüller space. So then the theorem is the locus of holonomy double covers of M is a geminal orbit closure. So one more reason to study geminal orbit closures is to study the complex geometry of Teichmüller space. So before stating the final theorem, I wanted to present one more non-trivial example of a geminal orbit closure. As you can see, this example is a 3-to-1 cover of a quadratic differential on a sphere. And moreover, the locus of covers to which these 3-to-1 covers belong have the property that every cylinder in them can be dilated while remaining in the locus of covers. This in turn means that the locus of covers of the surfaces inside M is geminal. So this is an example of a collection of surfaces with, it turns out, a rank 2 orbit closure, which have the property of being geminal. So this, together with the Wollmilchsau, suggests a sort of pattern which we established in this final theorem. So in an orbit closure is geminal implies that either it is a locus of double covers, the boring examples of being geminal, or a collection of degree bigger than 2 covers of quadratic differentials on the sphere. So this example, which is displayed here, is a prototypical example of the second case. So this theorem, of course, combined with the previous theorem that I stated, implies the very first one, that big orbit closures are loci of double covers. So theorem 3, which we just had, or maybe let's state theorem 2 first, says that being big implies that you're geminal, and theorem 3 says that being geminal implies that you are a locus of covers. I should also say the second case does not occur when the rank of M is bigger than G over 2, which is needed to get theorem 1 from theorem 2 and theorem 3. And so, therefore, this implies the first theorem that I stated, theorem 1, which says that being big implies that you are a locus of double covers, giving a positive resolution to the conjecture of Mirzakhani. And I want to end with an open question, which is related to the second question that I posed, which is, what are the loci of covers of the sphere that are geminal? So that's the final question I have, and that is my time, so thank you for listening.